Our fourth and final example for this lesson will have a slant asymptote. So how does that come about happening? Well, when you factor this one out, again, nothing cancels to produce a whole. If you wondered how I'm getting this factorization, remember you're factoring 4 to try to get 0x using subtraction. So that would be 2 minus 2. Okay, so you have x plus 2x minus 2. That gives you negative 4 and a 0x middle term. And on the denominator, you have x minus 1. So now the question is, why is there no whole? Nothing cancels, so that does not exist. Can there be a whole with the slant asymptote? Absolutely. I just didn't want to make our first example have too much going on. I want to focus on the slant. So your vertical asymptote, again, will be to set the denominator equal to 0. Most students are pretty good with that, and I got to be honest with you, when you start your assignment, maybe just do that first. You just simply set the denominator factored equal to 0 and solve, and you get x equals 1. They are, in fact, the domain restrictions as well, assuming there's no holes. The holes are also domain restrictions. So how do you find the horizontal asymptote? You compare the degree of the numerator to the degree of the denominator, and if the denominator has more, if the denominator wins, then what happens is you have to do long division. So in this case, this does not exist because the numerator has a larger degree than the denominator, and the slant asymptote will happen because you can actually, for the first time, you can really divide this into here and find an actual expression. Please remember that 0x we just talked about with factoring would also go here. So you can use long division if you want, right? You can do it that way, or you can do synthetic. I greatly prefer synthetic. So I'm going to do it that way. Synthetic is much faster and yields less mistakes. So synthetic, remember, works by taking your lead coefficient of your square, your x, and your constant terms, writing them in the synthetic division box, and then setting the denominator equal to 0 and solving, which ironically is the domain restriction, right? You just set this equal to 0 and solve, and you get 1. And then you add everything in the box to the bottom row. You never have anything in the first one. So 1 plus nothing is 1. And then you multiply, right? You're going to multiply this number here, 1, times this number, and write the answer in the box here. Then you add 0 plus 1. And then you multiply again, 1 times 1, and put that answer there, and that will give you your final answer of negative 3. And then the question now is, well, what does all this mean? Well, x squared will reduce by 1 to become x. X is a constant, and this is the remainder. And your slant asymptote will always come out in the form y equals mx plus b. And you probably say, well, how is it possible if I have 3 terms? Well, the remainder doesn't matter for synthetic division when you're doing asymptote. Sorry, let me say that again. The slant asymptote does not require the remainder. So you actually just get y equals x plus 1. Now, why doesn't the remainder matter? I'll just tell you it has something to do with something called a limit, which you will learn about in pre-calculus. And the limit of this remainder is 0, so it doesn't actually end up mattering. Okay, so now we're going to take a look at the x-intercept. The x-intercept would be to set the original problem equal to 0. So that would be x squared minus 4 over x minus 1. And then you multiply by the least common denominator on both sides, which would cancel here and make 0 there. And then you end up getting 0 equals x squared minus 4, which we already know what that is because we've already factored that. So 0 is equal to x plus 2 and x minus 2. And if I set both those equal to 0, x plus 2 equals 0, and x minus 2 equal to 0, I get x equals negative 2. Here I get x equals 2. And so my x-intercepts are negative 2, 0, and 2, 0. And then my y-intercept would be to find f of 0, which would be 0 squared minus 4 over 0 minus 1, which would be negative 4 over negative 1, or 4. So my y-intercept is, I plugged 0 in and got 4. So the chart doesn't change. I'm still going to use it to find missing values, but let's see what we have now. So we have a vertical asymptote at 1, right? Our vertical asymptote here is at 1. Our slant asymptote is an equation of a line. So if I were to graph this line, right, it would start at 1 and then go up 1 over 1. So start at 1, and then just like in algebra 1, right, start at 1, go up 1 over 1, up 1 over 1. You could also go down 1, back 1, down 1, back 1. And that asymptote is it's the equation of a line, and it's slanted, and that's why they call it a slant asymptote. I kind of just wish they called it a linear asymptote, but technically a horizontal line is also linear, so that's probably why they call it slant or oblique. Okay, so now we have our X-intercepts. We do have 2 of them, so that's convenient. If you recall, they were plus 2, 0, and negative 2, 0. So negative 2, 0 and positive 2, 0. And our y-intercept was 0, 4. So we have pretty good information there. So let's see what we have. Our vertical asymptote is at x equals 1. Wouldn't hurt to label these, right? So this is x equals 1. This is the equation y equals x plus 1. Y equals x plus 1. Okay. So now going to the left of this, just like we have going along the x-axis, x equals 1 does not exist. So going to the left, we would have 0, and then negative 1, and then negative 2. Well, we already know negative 2 is 0. We already know 0 is 4. And then going to the right, we have 2, 3, 4, 2, 3, 4, and we already know that 2 is 0. Sometimes you get more out of your work than other times. So to do negative 1, again, I'm always going to go to this factored version. I mean, I don't know, maybe you do this one this time, but I want you to see this way of simplifying, because it just is very important. In calculus, there's a lot of table analysis, so I just wanted you to see this. So negative 1 goes in here and gives you 1, and here it gives you negative 3. So negative 1, negative 3, and negative 1 goes in here and gives you negative 2. And so this would be overall 3 over negative, you're multiplying. So negative 1 would be, that's a little mistake there. How did I know there was something wrong? Because this couldn't be negative if these two are positive. So negative 1 is 1, and then negative 1 here is negative 3. So yes, this will come out to negative 3 over 2, which is be 3 halves, or 1.5. That point makes sense. Make sure your numbers make sense. Of course, you can use a calculator to help you yourself out if you need it. So here, if we put 3 into this, we would get 5. And if I put 3 into here, I would get 1. If I put 3 into here, I would get 4. So that's 5/4. And then if I put 4 into here, I would get 6. And 4 into here, I would get 2. And then 4 into here, I would get 3. So that's 12/3 or 4. All right, so let's just make sure everything trends correctly. If it doesn't, we'll have to just double check. So 1.5, so negative 1, 1.5, perfect right there. 0, 2, 0, and then 3, 5/4 is 1.25, and then 4, we're at 4. So it's looking good. And again, so what does this do, right? This is going to curve towards my axes, right? So my axes are here, and I'm going to go through these 3 points and then curve towards my next axes. And then this one is vertical, right? It's a vertical asymptote here. When I said axes, I meant asymptote, and then come through here. So this point right here looks a little weird. So let's just double check. If I put 3 into here, I get 5. 3 minus 2 is 1. It is a little off. And you might have seen that. I didn't catch it. This is supposed to be a 2. So it should be 2.5. And so now it's right, ironically, right where it's supposed to be. So if you ever have a weird point like that, just double check. Again, I simply subtracted wrong. 3 minus 1 is 2. I accidentally added. I guess I was tired. All right, so our domain we could have done beforehand. It's always going to be everything except the vertical asymptote. You can see it here. Beep, stop, beep. So we stopped only at x equals 1. So x cannot equal 1 because I stopped my domain there. Now I want you to think about the range. Why do we have to look at the range all the time? Because students, it doesn't stop anywhere, but there's no way to know that from given information. Like if I start at the bottom of the graph here, beep, it never stops. So your range is not something you can just do from the information. The range is either y is all the real numbers, okay, or the range is negative infinity to infinity if you use interval versus set builder. In behavior, you also don't know with slants, right? It really helps. You have to have a graph. You can use test points, which is what that table is, and you can see the points are trending lower, so you could make that inference, but obviously a graph is a better way to do it. So once you see what's going on and you label the arrows, this arrow at negative infinity, the graph is going to negative infinity, and this arrow at infinity is going to infinity. Okay, so you can't tell what's going to happen until you make the graph. I know this is different than the other ones, but the only thing that's different is basically the horizontal asymptote that was horizontal has now been bent this direction, and then the graph will correspondingly bend around it. All right, so that completes everything we needed for this particular chapter, and I hope that it's a lot of information. I hope that you go back and watch some of the videos again if you need to, because it is a lot of information. But each particular piece of information is not too difficult. It's just a lot to do. And I just make sure you go back and maybe start back and look at the vocabulary part of it to make sure the vocabulary part makes sense.